Hello, we are presenting Porti-Dump, and the contributors were Evan Lugo, Jake Kim, and Alejandro Bohon. The objective for this project is to contribute towards creating a cleaner environment by using machine learning and mechanical design concepts. For our application, we specifically chose the beach environment. To do so, we designed an autonomous vehicle that is capable of detecting bottles amongst other objects and scooping them up. We want our design to operate under minimal power and processing requirements. And additionally, we want this project to save time and money by reducing the amount of man hours that are needed to accomplish a repetitive task.
The three main components in our beach cleaning robot consist of computer, electrical, and mechanical design. The computer aspect of the design incorporates machine learning and object detection. The electrical part consists of selecting the proper motor and microcontroller. Lastly, the mechanical component includes choosing the right material and creating the entire model for our driving mechanism. We will go over these sections in order and explain the fundamentals that led to our design.
TensorFlow is an open source platform for machine learning that has a variety of comprehensible tools, libraries, and community resources. With TensorFlow, it's easy for beginners to build and train a machine learning model using APIs like Keras, which makes for immediate model iteration and easy debugging. In our application, we use TensorFlow to create and run an object detection model, as well as its many tools to monitor the progress of the training.
OpenCV stands for Open Source Computer Vision Library, which is essentially a library of programming functions aimed toward real-time computer vision. In simpler terms, it is a library used for image processing and object detection. Given an input image, we want to obtain certain criteria such as a list of bounding boxes, which determines the XY coordinates for each object in an image, the class label associated with each bounding box, and the confidence score, which represents the minimum probability threshold to filter weak detections. In other words, the accuracy of the object. In our application, we set the confidence level to only detect objects that are greater than 40%. Before importing data and images into our Raspberry Pi, we want to get a better understanding of how OpenCV works by initially testing color objects. In our case, we chose the color red. The video we are about to present shows a demonstration of how the stepper motor is controlled using Raspberry Pi and the Pi camera. Using the same concept with contour detection, we want to implement a similar method shown in the video to our design once we import and create a path to a pre-trained model so that the stepper motor can move depending on the location of the bottle. As shown in the video, the stepper motor rotates based on the location of the object to allow the motor to adjust itself until the red object is in between the two boundary conditions that we created. If the object is located on the right of the camera, then the motor rotates clockwise to center itself. If it is on the left side of the camera, then the motor rotates counterclockwise to center itself. Once the object is detected in between the two vertical lines, the stepper motor continuously rotates to allow the vehicle to approach to the desired target. In other words, those boundaries are another way to help navigate the position of the bottle. As mentioned before, since we were able to get the color detection to move with the motor, our next step was to use the same concept when a bottle is detected for our application.
When creating a model, there are a few requirements. One being the TensorFlow Object Detection API, which is a structure for the files and records that are being stored during the process, a set of training data as images, and a training model. In essence, the training model is being fed hundreds of images with specific known labels during the training, and then it's tested. The longer the model is trained, the more the accuracy improves. In our training model, we use a convolutional neural network, which is a deep learning algorithm that takes an input image, assigns learnable weights and biases to the various aspects of the objects, which enables the model to differentiate one object from the other. Since we're using a Raspberry Pi, we specifically use the SSD Lite mobile net model because it has less of a demand in processing power. As a result of this, we get a higher frame rate speed by sacrificing some of the accuracy. The image above is one of the various images we use in our dataset when training the model. Using a specific labeling program, we drew boxes over every image and saved it along with an XML file containing information about the class, width, height, and so on. The two lower images are some of TensorFlow's features, allowing us to visualize the progress of our model being trained. The graph shows us the amount of losses over the epoch, or the sample batch. So over time, we're seeing the amount of losses in our model reducing. So we broke down our code into the structure of it to make it a little more understandable. We first import the packages needed to run the rest of the code, and then set up all the parameters for the stepper motor and the Pi camera. Afterwards, the TensorFlow model is introduced, and this consists of the trained model, the inference graph, and the labels used to classify each object. The last two parts of the code initialize the PI camera and the stepper motor to control the direction in which the vehicle turns. In simplest form, the frame of the camera is passed through the object detection model. If a bottle is detected, it'll execute the stepper motor control. Once 20 bottles have been collected, the program will stop and shut off the vehicle. In the video, we can see the motor moving similarly to when we use the contour plots, but instead we're using the object detection model. Although the code functions properly, we had trouble increasing the speed of the motor due to the low frame rate that was between 0.8 and 0.7 seconds.
The mechanical design consists of both a tank as a driving mechanism and a conveyor with a basket attachment. The idea is that once the water bottle gets detected, the tank will pass over the bottle and get ramped up into the conveyor and back into the basket. The conveyor system is composed of the following equipment, adding up to a total of about 20 pounds. The conveyor belt itself is designed wide enough to accommodate any unwanted movements, and in addition was created with lips and a low enough angle to prevent any rollback. Perforations were made to prevent any sand to pass through to the basket, and the basket was designed using marine vinyl, which is a material that is waterproof and sand won't stick to. Similarly, the tank is designed with the following equipment, adding up to about 8 pounds. The tank drive was chosen due to its good traction on sandy surfaces, running on two motors. It was also designed with a high enough clearance to allow any water bottle to pass at any orientation. And in addition, the camera is located at the front with an angle to allow focus on a particular object at a desired distance. For the driving mechanism, the tank consists of a front two-wheel drive where both motors activate simultaneously in order for it to advance forward. If a turn is desired, one single motor will activate while the other remains idle. The conveyor drive is assembled with no motor and thus only being hauled. With a total weight of about 10 pounds per side, a desired torque of 140 ounce-inch was calculated. In order to accommodate for any frictional losses like sand or hills, a motor of 178.5 ounce-inch was chosen. In order for the water bottle to get caught by the conveyor system, a fast enough speed was required in order to create momentum of the water bottle. With a desired speed of half a foot per second, that gave us a necessary 65 RPM per motor. For structural integrity of the design, we set the failure mode to be the link tab that connects the tank and the conveyor. A static structural analysis was performed to determine the total deformation, the von Mises stress, and the factor of safety on the following three components. Since the frame is the main component of the entire system, it was set to have the highest factor of safety at 15 with a total deformation of 1.1 times 10 to the negative 5 inches and a total von Mises stress of 195 psi. The link tab was set to be the failure mode in our system, giving us a factor of safety of 2.02 as the minimum, a total deformation of 0.056 inches, and a von Mises stress of 3,885 psi. The second failure mode was the linkage, giving us a minimum factor of safety of 4.9, a deformation of 0.025 inches, and a total von Mises stress of 1,595 psi. The grand total for the project ended up being $324.57. We can also improve our designs in the future by increasing the frames per second in our model. There are attachments that can be purchased to connect to the microcontroller to enhance the rate of frames per second. In addition, we can train object detection from scratch to take out unnecessary classes in order to reduce the processing time and not waste any memory on the Pi. Additionally, we can also attach a pressure sensor to scale the weight of the bag instead of using a counter in our code to count how many bottles there are in the bag. There may be cases where the bottles are not fully empty and it may reach a weight threshold, which can result in damages to our mechanical design. We can also add additional sensors to have smoother control of the vehicle. Due to the limitation of size, another future improvement could be increasing the volume for the carrying capacity of water bottles, as well as increasing the rigidity of the conveyor frame itself.
Here we have a few references that aided us when designing the code and learning about the topics covered. Thank you all for your time.